Yeah,
I studied in Uttarakhand, so I know I've visited that Almora campus where you studied.
I see. Great.
And
Perfect.
very happy to see that achievement recently of that the experiment that was conducted for secure quantum communication.
Thank you.
I'm sure you will share that in the
Yeah, I will just talk few things because the title. I have seen that RP was already talking about free space communication, so I thought that let's not repeat those things. But I will just tell you a few things, or maybe sometime in future we can discuss more on that part, because this is completely different domain than fiber-based things. And today it was more about doing fiber-based communication and fiber-based, quantum key distribution kind of areas. Yeah.
Dr. Rajendra Mitterwal also joined, sir.
Hi. Hi, nice meeting you. Yeah.
You have interacted with him as well.
Yeah.
He's the principal coordinator for this course. And
so tomorrow is having a lecture tomorrow, or it's finishing in 2 days, I think.
Right. Yes.
I was asking
today
it is finishing in 2 days, or when it is finishing this particular.
Tomorrow is the last class.
Yeah.
Tomorrow we have an industry lecture, not industry lecture by, I think, Professor Dr. L. Venkatasubrahmanyam may join, but Professor Anil Prabhakar from IIT Madras, he'll be concluding because he's the quantum hub thing, so he'll be concluding.
I see.
Today is Kavita ma'am's birthday also.
Oh, so happy birthday, I would say. Really.
We will meet you sometime and interact also. We are in Delhi. We are in Jaipur. You are in Delhi, so
yeah. Sure. We will do that. Sure.
We will start the second half. Thank you so
So
much.
I think my screen is already shared, or it's not shared.
No.
Not yet.
Okay.
Yes.
Shared slides.
Stop sharing content.
So I think you can see it now.
Yes, sir. Now it is. Sure.
Okay, so I will try to finish in 50 minutes, 40 minutes or something, so that we can have some more interaction from these questions, because some students have some good questions also. Yeah. Okay, so in this particular section, I will focus on the hardware aspects of quantum encryption and secure key distribution. And essentially here, the more focus would be some of our activities in the domain of quantum optics, quantum communication, and quantum key distribution nowadays. So at IIT Delhi, we are essentially in physics department, and our group is called EQUIP, which is experimental quantum interferometry and polarization. And our activities are spread over several domains, which include free space quantum communication, where the goal is not only to do quantum key distribution using preparand measure and entanglement based resources, but also to use partially coherent sources for making better sensors, especially using the quantum properties. In this picture, you could see that we're talking about this free space communication. So this is the actual picture, Google picture basically, of the research park. This is one of the buildings, and the other one is the main building, which are about 500 meters apart. So we did it a communication. So we started actually this free space communication first within the research park, probably last year, and then slowly we moved further. We went for 100 meters, and then 500 meters, and then finally 1 kilometer very recently. And then we are connecting these two buildings essentially, and in between you could see there is a ground also, where basically it's an area where a lot of optical this air turbulence or medium turbulence occurs. However, we were able to show that this urban environment can also make this quantum communication possible. I mean, there is no way that in urban areas with more pollutions and more turbulences, we are restricted. We can still do that. So these were some of the activities in this domain. Then in fiber-based QKD, as I already talked in previous session, that we are aiming for telecom compliant preparand measure and entanglement based QKD applications. One of our main domains are to develop single and entangled photon sources, where we aim to have more brighter and higher rate with higher purity. This is one example of our recent work where we have shown that we can actually work at time domain. That means we can take very, very small ultra fast pulses at a very high rate, typically up to 20 gigahertz. And we can show that we can achieve the single photon properties with very, very high purity, which is 0.0003, essentially the minimum values which we could achieve. So these are some of the areas in this domain. And finally, we are also collaborating with people who are working in material science so that we could develop materials, especially for high temperature, high critical temperature, using superconducting nature, so that the superconducting single photon detectors could be developed. And the aim is also to make them photon number resolving so that they can tell that how many photons they are detecting at a time. So in this particular section, I will more focus on the sources and detectors which we have been developing using for quantum communication, and then some of the demonstrations which we made for QKD both in lab and in the field using fibers. Then how we were developing entanglement based sources, how we were distributing them, and how QKD was being done, and what kind of networks people are trying to aim, and then how can we look for the quantum hacking aspects and provide countermeasures to the attacks, especially being done for QKD systems. Okay, so this is just a snapshot of the kind of activities which are being done in the domain of quantum communication. So there are three ways one can understand it. One is the preparation, where the goal is to prepare the quantum states, which can be either done in a discrete variable domain, which essentially means you are using some of the properties which are countable, such as polarization. We have horizontal, vertical, diagonal, anti-diagonal. Similarly, we can also do continuous variable cases. Continuous variable essentially means that the properties which we are looking at, they are not countable. For example, is such as the the quadrature of optical fields. So you can measure amplitude and phase, which is a continuous function. There is no discreteness in that. Similarly, you can have a quantum channel which can be either optical fiber, which is essentially using a glass fiber with having certain limitations in terms of distances. First of all, it has a attenuation, so a standard attenuation is always there. The polarization is not preserved, so you have to find ways by which you can preserve the polarization. And also there is some scattering sometimes if the fiber is bent, for example. Then we have free space optical systems, where the distance is limited because of the curvature of the earth, because since the earth is round in shape, you cannot go straight. You have to at some point bend, and light doesn't bend, and that's why you cannot go for very long distances. There is atmospheric attenuation, there is turbulence, which I was mentioning, and also there can be blockages in line of sight because of either trees or some mountains or any other kind of man-made structures as well. So one has to go for satellite then, and in case of satellite-based free space optical communications, then the atmospheric attenuation and turbulence plays a very important role, which can block essentially the communication. When we look for the measurements, we have for discrete variable systems, we need to measure essentially photons in terms of their counts. So we need clicking detectors, which are called single photon detectors, and they basically give some switching effects like on off or some such effect which can be counted. And that tells you how many photons you have detected. On the other hand, you can also use continuous variable kind of detectors, where since you need to measure continuous variables, you need to measure either using methods of homodynamic and heterodynamic. I will not go into the detail of that because in our talk today, we are focusing on discrete variable, optical fiber with discrete variable measurements. Now, how a QKD hardware looks like. So you have a QKD source. The source is the complete source here with Alice. This includes some optical sources, which can be either a laser or it can be a process of SPDC, which I mentioned. You need some timing control using or RF control using FPGAs in general. Then you have some basis generation, which can be either done using phases or it can be done using polarization. At the receiver side, there is a quantum channel in between, whether it can be fiber, it can be free space, and the signal goes to the Bob side, which is a receiver side, And here also you need some timing and synchronization between Alice and Bob, which can be done using either a fiber or using some GPS kind of synchronization, depending on the requirement of precision. And then you have also the basis here. The basis can be the similar way, you can put the exact basis and figure out whether the photon is coming in one basis or the other. And then also you need some control in terms of polarization or phase, so that you do not scatter the information to different polarization or different phases. Now the two parameters which I already mentioned in the previous talk are the key rates and Q-bar, which you need to look into. If the Q-bar exceeds some threshold, you stop the communication, because you know that somebody has tried to steal the information. Now imagine, I told you about attenuated laser source in the beginning, in the last talk, which is also called weak coherent pulse source. And this easiest way is to use a laser with a set of pile of glass plates, where each plate is reflecting some portion, so the total outcome is attenuated. Then you can use a beam splitter and you can measure the detection in one side. So it has a Poissonian distribution, and if you see here, this is the probability of having one photon, zero photon, and many photon. So whatever kind of input or mean photon number you take, you see that you have always a finite probability of multiphotons. So a Poissonian distribution tells you that you have always multiphotons. So there is always a possibility of photon number splitting attack. So this is why protocols which are using multiple photons are avoided, because they would have a larger probability of eavesdropping. And DPS, I mentioned already, is one of the protocols which we used. Since here the information is distributed in phases, the information is not just in one pulse but in several pulses, the photon number split is not easy to do. And in fact, people have shown that when anybody tries to do a photon number splitting attack, then the Q-bar would exceed more than 50% and you can easily catch it. And this is why DPS is sometimes considered to be a very safe one with photon number splitting attack. So we had looked into this protocol in the beginning of our work, where we tried to develop it in the lab. And since it was very useful for fiber-based quantum channel, we thought that we will try to do a field test also with this. So this is the scheme which we developed in our lab sometime in 2020-21, where we were interested in a DPS QKD. And as you could see here, we have Bob here, Alice in this side shown here, and there is a quantum channel in between. There are spools of fiber somewhere put under the table, which are more than 100 kilometers. So the actual length we worked is 110 kilometers. The modulation rate was 800 megahertz, and the Q-bar which we achieved during the QKD was 4 to 6%, and a rate of 15 kilobits per second was achieved. Then we decided to take our system, transmitter and receiver, to a place, a stretch, basically fiber stretch, where a long fiber of more than 100 kilometers was available underground. It was between Prayagraj and Vindhyachal. It is close to somewhere in east side of Delhi, of India. So now you see that our transmitter Alice was at Prayagraj, our receiver was at Bob. The fiber had 100 kilometer distance with a loss of about 26 dB. So you see that if you determine per kilometer loss, it is 0.26 or 0.25, contrary to 0.2 dB, which is in a bare fiber in the lab. So in field, the losses are a bit high. And this was a joint effort with DRDO team as well. And we have shown that with this distance, we can get a Q-bar of less than 9%, which was well below threshold, and a key rate of up to 10 kilohertz. And then we used FPGAs for clock synchronization between transmitter and receiver. And also we feel that since it was the first such demonstration in India for such a large distance of 100 kilometer, we could actually go for long distances like 2000 kilometers by repeating this 100 kilometer stretch by 20 times. So basically you can put trusted nodes, and by putting those trusted nodes, you can go for long distances, and it can work as a backbone for a network for such kind of long distance. But the question which we asked afterwards is that whether this is the maximum distance, like 100 kilometer only one can go, or one can go even better or larger distances if these parameters can be improvised. So we looked into those parameters which were essentially contributing for Kuber and key rate, and we found that the total Kuber is essentially the sum of three contributions. One is because of the interferometer which we were using. I told you that there is an interferometer which is used. So this interferometer is the main part. So we tried to basically look into the effects which were increasing our Kuber in Maxender, the Kuber due to dispersion of the fiber, and the Kuber due to the dark counts in the detectors. And these are the three plots you see which are showing the role of all three in case of our protocol. So the Maxender has larger Kuber when the line width is larger. So we really need to look for a line width of kilohertz. The dispersion plays a very important role for large distances, and if we could put a dispersion compensating fiber, probably we can handle it. Now the dark counts depend. If you see that if the detector has a very low dark count, the distances can be up to 70 dB. However, if the dark counts are 500 counts per second, which was the case in our, the distances would be shorter and shorter. So you see that there are several parameters which play an important role in increasing the error. And if we could reduce them, for example, Maxender, we can reduce by reducing the line width. We can put dispersion compensating fiber. And for detector, we can use the advanced detectors which are having very low detecting dark counts. And these are the comparison of the detectors which are available. So if you see here, we have SPADs. Typically, these two columns are interesting for us because we are working at telecom wavelength that is around 1550 nanometer. So you see that the existing SPADs which we're using, which were based on InGaAs, they had a very low quantum efficiency, very high jitter, and high count rate, dark count rate. On the other hand, if we use a more sophisticated superconducting nanowire detectors, then we can increase in quantum efficiency, we can reduce the jitter, and also reduce the dark counts. So that means that they can be very important if we could bear the costs, because they are really very costly. So we procured such kind of detector in our lab in 2021, and here we had a quantum efficiency which was 8.5 times higher and a recovery time which was 120 times higher. And this is a very sophisticated system. It includes it works at a temperature of 0.8 Kelvin, that means 800 millikelvin, and also it is using a lot of vacuum and closed loop helium, and that sometimes really requires a lot of maintenance. So now our system is improvised. We are working at 2.5 gigahertz repetition rates. We are using a dispersion compensating fiber for this. The laser is having a narrow line width, and we are using superconducting detectors, and everything is still synchronized with FPGA. And if we do so, we have shown that we can go up to 265 kilometers of the fiber length with a Kuber less than 2.4% and a key rate of up to 193 bits per second when we are operating our detectors at the maximum quantum efficiency, which is about 88%. And the system is very stable. You see that this is the stability for 5.5 hours, and there is hardly any fluctuation, less than 5% fluctuation over this duration, both in secure key rates and in Kuber. So we are at very good situation now. We are working at very low Kuber instead of 9%. But the question is whether this is the maximum or we can still push it by using the property of the superconducting detectors. And the property says that by operating the biasing point and shifting it, we can play with the dark counts and the efficiency. So we thought, okay, let's reduce the dark counts from 50 to 100. We can go up to 1 per second kind of situation, and see, though our quantum efficiency will decrease, we can still see that what kind of outcomes we can get. So now in this situation, when we started with at 1 count per second count rates, dark count rates, we get a Kuber of even less than 1.5%. That was one of the lowest Kubers reported so far, with a key rate which was quite low because our quantum efficiency was compromised. But we could go for a distance of 380 kilometers. And if instead of this standard fiber, we could have used a new kind of fiber which is commercially available nowadays called ultra low loss fiber, where the losses are 0.14 dB per kilometer. We could have gone up to 432 kilometers. So these are the results which you could see in this work, and this is the paper which was published in some good journal. And you see that these are the other works which people have done over last 20 years with these protocols, with this protocol. And our distance was the largest achieved with the least cuber, if you see here. And also we were operating at a pretty good clock rate. And the good thing here is that now if I use it for 380 kilometers in one stretch, for going 2000 kilometers, I do not require to repeat 20 times. I need to require only probably 6 times. So I have reduced the trusted nodes significantly by doing so. That means the loophole of security is significantly improved now. And our attacks can be also reduced significantly. Further, we also looked for entanglement, which is one of the key resource, and we use the process of SPDC, which I explained before. In fact, I would like to mention here that entanglement has been a useful resource. It's not just people have demonstrated in the lab, but these are three gentlemen, and they not only proposed how to measure entanglement, they did it first time in the lab using photons, and later on it was used for many applications by the third gentleman. And these three were awarded the Nobel Prize in 2022 for the entanglement related experiments. So we also went for this direction. We first used SPDC outcome for developing a heralded single photon source. In this situation, we actually measure one photon, and we measure the second order correlation property, which tells us that what is the probability of multiphotons. So you see that in a normal scenario, when we were working at 810 nanometer using PPKTP crystal, we could have a heralding rate of zero point 0.1 with more than 4 million counts per second. So at 4 milli Mbps kind of rates we were achieving with 0.1, and the purity needs to be as small as possible, and 0.1 is a pretty good number. However, we have also shown that if you go for 0.04, that is you are even more pure, then you reduce this 4 million to 240 kilocounts per second. And if we use another scheme which I demonstrated in the beginning, which was working at 20 gigahertz rate, we could go for a G2 of 0.0005, one of the purest kind of photons ever achieved, but then the rates are also compromised accordingly. So depending on the application, you can operate either at this or at this kind of basis point. Then we developed entanglement. These are the different scenarios how entanglement was developed. Somebody was asking in the previous case, how was your source? So these are all kind of sources we have in the lab. So this is at 810 nanometer for free space communication, and this one is an all fiber source at 1550. This is using periodically poled KTP crystal. For our 1 kilometer demonstration very recently for free space, we used this type 2 scheme, this kind of source. However, we have another kind of source which is more efficient, but we are using it for some other application. And this is a all fiber source which is working at telecom wavelength, which is used for all fiber based communication, entanglement based communication applications. In all the three sources, you see that the visibilities are pretty high, and the Bell violation, which is essentially a measure of entanglement, the value should be more than 2. In our case, the value is always more than 2.6, and the maximum theoretical limit is 2.8. So you could see that we are well near the maximum limit. So the purity of entanglement is really fantastic. And then how the source was developed. So this is a typical picture of the source. We are first we tried to make the photons indistinguishable, which requires the photons to interfere on a beam splitter, and this is the interference visibility. You see that we had about 96% visibility of interference, and then we looked into the total visibility in different bases, that is horizontal, vertical, diagonal, and anti-diagonal, and in all visibilities we could get these numbers. And finally, the Bell violation S value is more than 2.6. So now the photon has entanglement, and these two entangled photons can be distributed through fibers. So we use a fiber spool of 50 kilometer in one side, 50 kilometer in other side, and we distributed it. and we make the measurement of correlations and entanglement. So you see that these are some of the pictures associated with this measurement. For 100 kilometer, the visibility we could get was still more than 80%. That means we are well above 71%, which is a threshold for entanglement. And for 50 kilometer, we did several measurements, because when we did these experiments, we had only 50-kilometer fiber available. So you could see that for different lengths, the QBAR was significantly low. The coincidence rates were about 30 kilo for at the source, and then with distances they were reducing because of losses, and the key rates were also reducing, and at 50 kilometers we had about 1.4 kilobits per second kind of key rate with 2.77% QBAR. Then we decided to make it in the field, and thankfully at IIT Delhi campus, if you, there is a picture shown here, we have some fibers for internal intranet applications. So we requested one fiber from our computer services center, and that fiber has a picture which is shown here. It is about 8 kilometers length. It is underground. It is probably 30 years or more older, so it has huge losses, about 6.5 dB losses. So we use this fiber. So what we did, that we sent one photon through the fiber and detected back. The other photon was sent to a fiber spool of 10 kilometer. And for this whole setting, when we did our QKD, we got a QBAR of still less than 3% and a key rate of 2 kilobits per second. So you could see that in all lab-based as well as field-based settings, the entanglement-based QKD is compatible, and that can be used with the deployed telecom grade fiber. The getting a longer fiber is very difficult, especially in Delhi, and if we take it to somewhere else, then the detectors which are superconducting, they do not allow us to move, and this is why we are restricted to use fibers which are available within the campus or connected with the campus. Now, I also mentioned that after doing this point-to-point test, we would like to extend it for longer distances. So one possibility is to develop a, a network, something similar to what Tokyo QKD link was. As I mentioned, it was about 220 kilometers, and it has several small stretches, each with different type of protocol. Some are using, for example, from Vienna, some are using from Toshiba. Different companies has provided different kind of fibers. So this system is something which is a hybrid system in these protocols and could be a good alternative to go ahead with. Swiss quantum network is also very similar. It has a triangular kind of topology, and you could see that it is connecting three major institutions there with 10 Gbps of Ethernet encryptors, and ID Quantic was the company who actually used BB84 protocol in that. And these were some of the very early networks of last decade, and we would like to develop further in this decade networks which are even more promising. China has in between developed a 5,000 kilometer network. Already I explained about it. In each of the city, they have these small key distribution centers by which the clients can take the keys. So it is essentially developed in a model where you can use it for commercialization. And very recently, Toshiba have come up with these deployable QKD systems. And this is some very new and very advanced version of these QKD. As of now, they were the bulk systems, which were of the size of a 3U or 4U 19-inch rack. But what they have shown, that they can develop chip-based QKD, where every system, like a transmitter, is like a small USB device. Similarly, receivers and QRNGs all are small pluggable devices, and these modular devices can be plug and play, and that way they can be more rugged, especially for deploying the QKD for real applications. And we believe that this kind of technology would be required ultimately if we really want to use it for very sophisticated areas. So deployable photonic integrated circuit based robust QKD systems are the need of the hour. So now I would like to give you some perspective of developing quantum internet, that in case it is what is the process and how it can be developed in a given time scale. So if you look back and try to see the development of classical internet, which started first in the form of development of first electromechanical computers in 1950s, then the development and progress of integrated circuits and transistors in 1960s led to the development of the Mach systems in 1980s. In between, to connect these big systems, Ethernet and TCP/IP protocols were developed, which are still in use. In 1970s, they were developed, and in 1990s, these Mach systems were connected with Internet and www. This World Wide Web is still being used, so we are not very far from this place, if you see. And this development, if we look into in terms of quantum internet and quantum computer, we had some basic quantum computers developed sometime in the last decade, and we had also in this decade a rapid development in quantum hardware and quantum supremacy. We are also developing multi-node quantum networks here in this decade. In the next decade, we expect to have full stack quantum computers, and probably in 2040s, sometime well before 2047, we are aiming to have quantum full stack quantum computers connected with quantum internet. So now, in order to do that, as a precursor under National Quantum Mission, we are running a project which is called Towards Trusted Node-Free Hybrid Quantum Secure Communication Networks. In short form, we call it Tehqiqat, which essentially means to investigate through research. So IIT Delhi is a lead institutions, and as a lead PI, we are leading 5 other institutions, which are IIT Roorkee, IIT Jammu, IISc Bangalore, and ISER Bhopal. And the goal of this whole consortia is to develop a network which is a hybrid network. And in fact, this will be connecting 4 states, UP, Delhi, Haryana, and Uttarakhand, with 6 nodes. One node will be somewhere in Noida, 2 at IIT Delhi, one as free space and one as fiber. Then there will be one node at IIT Delhi Sonipat campus and 2 nodes at IIT Roorkee, one fiber and one free space. And in total, there are 6 nodes. And if you see, this is a kind of a hybrid test bed, because we are not only trying to have entanglement as a protocol here, but also non-entanglement prepare and measure protocols are being used. So it is hybrid in both protocols. It is also hybrid in channels, because we are using fiber channel as well as we are using free space channels. So we believe that with existing technology, the kind of available infrastructure where both free space and fiber based QKD is being developed, there is a need of integrating all of them, and that can lead and way forward for quantum internet. Now, if you look into the some commercial QKD products which are already available on the market, so some of those I have listed here. In fact, there are plenty of startups have come up with again different type of systems, but these are some early systems which were developed and they were using different type of protocols. For example, this Magic Tech was using BB84. This Clavis 3 of ID Quantic still uses COW protocol, current one way, and also this SecureNet is using continuous variable kind of protocol, and the distances typically 100 kilometers they promise, so you can always put repeated such systems to go for longer distances. And this is how internally the systems look like. So you have a lot of fiber, you lot of electronics, and all these control systems. So now, as I mentioned, that since a lot of electronics, fiber, and optics is involved, they are prone to what we call quantum hacking. The hacking is not through the principles of quantum physics, but the hacking is because of the side channels or the other kind of hardwares which is not following the exactly the theoretical definition. And that is pretty sure, because whenever we theoretically assume something, we always look for perfections, but experimentally there are always some shortcomings, and the devices may not work as perfectly they are intended to be, and that may open some parallel channels which can be used by hackers to attack on the system. So, in fact, there are ways by which people are coming up with ethical quantum hacking. That means there are people who are trying to probe these systems in an ethical way with a permission, so that they can look for the attacks and propose some countermeasures. So, this is an area which is developing very, very fast. And the intention here is to improve the security of the existing system, and to provide where the loopholes are and how they can be mitigated by providing countermeasures. So there are several kind of protocols which has been proposed over last 10 years time, and also their targeted element, which is either a detector or optics or some modulator or beam splitter, they were pointed out. And also the systems which were developing them were also told about these loopholes so that they could improve it. And this happened with ID Quantic. For example, they came up with Clavis 2, and there has been several attacks which was proposed, especially by this group, on Trojan horse. And later on they improved by their advices, put some countermeasures so that the system is came up with name Clavis 3, and it is much more secure compared to its previous version. So some such attacks I am listing here. There is one something called blinding attack. Here the goal is to blind the detectors. So it can be done, for example, if you are using a polarization based system which is either working with horizontal and vertical polarization. If you give as an attacker a circular polarization, then the detectors would see it sometimes horizontally, sometimes it vertically. They are blinded on that. And that way, by using that light, you can get the information of the basis which is being selected, and that way you can recreate that as an attacker at your own place. Similarly, the SPADs, the single photon avalanche diodes, which are used typically for measurements of single photon, they work in the Gregor mode. And if somehow you put a very intense laser beam which damages the detector, then they drive driven toward the linear mode instead of the Gregor mode. So in that way you can play with the settings of the detectors, and that way you can drive the device in your own ways. And that way many commercial systems which are vulnerable to this attack can be identified. And the countermeasures they were proposed, for example, are optical isolators, by which you can isolate the device to have some less than some threshold power, and that way you can avoid these kind of damages. Similarly, there is an attack called Trojan horse attack, and this is typically taken from the name Trojan horse historically. So here what happens that each of these optics which is being used, they have some back reflections. And if you send a light beam in a reverse manner and you try to look into those back reflections, they can give you some information about the settings of those components. So it has been tested by people that these back reflections can give you the idea about the settings of your device, and that way you can actually know about the keys. And then they propose that you can use some countermeasures, such as you can install a watchdog detector, or you can isolate and put a wavelength filter, and that way you can save your scheme from these kind of attacks. Now, before I finish, I would like to mention that the kind of tabletop systems we have developed very recently, we came up with a startup where we are making prototypes and commercially available solutions from these proof of principle technologies. And the startup, the spin-off is Qubitonics Technologies. So here we are having the goals of developing elements of quantum networks such as single and entangled photons, fiber and free space based QKD solutions. And a major portion we are aiming is to develop hands-on kits or lab experiments, especially for training skilled manpower in quantum physics or in quantum technologies. So as we know that in India, there is a very less portion of human resources available with skilled experimental technologies or experimental hands on these sophisticated technologies. So one of our goals is to develop such kind of experiments or hands-on devices or kits which can be used for understanding or testing, doing hands-on in the labs with these areas. And these are some of those correlated photon sources or entangled photon sources which we have developed recently. And if anyone is interested, then this is the website, and you can go and see what kind of outcomes our we have developed so far in this area. So to summarize, we started with the aspects of QKD hardwares, and also gave you some understanding on single and entangled photon sources and how one can develop them, and what kind of features they offer. Then we have shown you the development of quantum key distribution, especially how we can demonstrate QKD in the lab settings, and then when we go into the field, then what kind of parameters they can offer, what kind of problems they associated with these devices can be seen. And finally, we talked about entanglement based QKD and QKD devices, and finally how one can hack these kind of QKD solutions, and what kind of countermeasures can be used to avoid hacking, and to make them more secure with their existing settings. So I would also like to thank our funding agencies, which are DRDO, DST, Government of India, National Quantum Mission, and IIT Delhi Institute of Eminence. And also I would like to thank the main workforce of our lab, these smiling faces which you see on your screens, which have been the main drivers behind these developments and these technologies. So with this, I would like to thank you, and if you have any questions, I would be happy to answer them.
So there are few questions on the screen, probably. I'll just read out.
Yeah, I will just go one by one maybe. So should I go at the top?
So
So
the first question is, on a side note, QNet has demonstrated quite a long fiber-based QNet. I believe in New York, they have used commercial network as best claim for feasibility demonstration. So this is, sorry, this is not the question, probably. There is one question which is turbulence rule for QBER.
so I don't see that one. So yeah, so when you say turbulence, then it is much more on free space, not on fibers. And turbulence is significantly deteriorating the real efficiency of your network, because the beams which we are sending optically, they move from their direction once there is optical turbulence. So if the pointing beam pointing direction, that basically fluctuates significantly from its actual direction, and if the turbulence is very high, it moves away from its direction significantly, and that way it limits us to be detected at the other side. So this is a big problem, and this is why we need to use, especially when we go for very long distances like satellite or long distance free space communication, we really need to come to find ways by which we can compensate for this jitter or this beam pointing fluctuation. And normally people use automated systems which can feedback, and can try to track the beam on its own automatically, and that way we can reduce the effect of the turbulence. Yeah.
So the next question is, what is typical secure key length used for the experiment?
No, so secure key length is the outcome of the experiment. It is not what is being used as a input, and it depends on what kind of protocol you are using, or what kind of length you want. So typically, for example, we can generate a key, secure key of 50 bits also, or a key of 1000 bits also. So it depends on. I mean, if we need a longer key, we need to wait for a long time, because we need to accumulate those many photons to get that rate. Otherwise it's up to the uses. If you are using it one time pad, probably 100 bits are also sufficient, but you can, since you are going to use it once at a time.
Okay, so somebody asked it's a line of sight, but then you are, I mean, it's already answered that it's an optical fiber-based communication. So
Yeah. So some
somebody is asking,
uh,
8 kilometer length stretch said about IIT Delhi related to what aspects?
So yeah, so I said 8 kilometer in fiber. So we have two ways to do it. One is free space, where the distance maximum we could go is 1 kilometer between two buildings. But we have also a fiber within our campus, which is round within the campus, connecting different houses. that the strength is 8 kilometers in fibers. So these are two different things.
Okay. So next question is, given the limited length of optical fibers in experiment, is it possible to form a closed loop of say 100-kilometer fiber channel and test the single source photons to travel in a closed loop for hundreds of kilometers before introducing the detector and making a final measurement? There might be practical challenges, but the idea just occurred and would like your comment on this.
But I do not understand what is the purpose of this. If it is a closed loop, then the photons will enter and then it will not come out basically, because no, it will keep revolving. And if it is coming out, then it will not be a closed loop. And going 100 kilometer would have a loss of 20 dB. That is the minimum loss I'm talking about. So you have to send a good amount of photons to reach some significant amount after 100 kilometers. But in a lab, you can always go for any length by putting the fibers. For example, if I can put, I have available fibers of 500 kilometers, so I can go up to 500 kilometers without any closed loop.
Okay. So somebody is asking, is it little over ambitious to think of a quantum internet at this juncture?
Really not, because when we are developing quantum networks, which is the actual practical application, and people are developing quantum computers, irrespective of whatever qubits they have, if you want to connect two computers, you need internet. Otherwise, you cannot connect them. And if you want to connect computers from India to connect computers from, let's say, US or Europe somewhere, then you really need some, because the classical internet cannot work with qubits, it works with bits, so it cannot connect with quantum devices. And not only that, quantum internet is useful for connecting quantum sensors, and this is a very big area. And quantum sensors will be available probably in next few years, which still require a distributed setting, secure communication among them, and then again you need quantum internet.
Okay, so the next question is, after receiving the end, what do they do, as we don't have a memory storage concept?
No, so memory is not required as of now. Memory is required for repeaters, because in repeaters you need uh, to to store the photons which are already moving. When we are talking here at the communication, we are detecting those photons and then they come out as a electrical signal. Then you can always record it in a different memory. The difference is that in this case, the memories are required just to store a digital information, which we are already doing. Whereas in the case of repeaters, you need to store photons, which cannot be stored as a stationary object, because they are always moving. That's why you need a different type of memory which can pass those photons but delay them significantly, such as using this EIT or some other kind of methods. So probably this question is talking about non-repeater scenarios, what I understand.
Yes, okay. So why the next question, while transferring data between quantum computers, if data is lost, how can we recover it? Consider Alice and Bob communicating with each other. Suddenly, a hacker tries to steal information from Alice, and as a result, some information is lost. How can Alice restore that information, and how will it remain unique? If Alice and Bob detect that something has gone wrong, how can they determine whether it was caused by hacker or some other error?
No. So I think there is a confusion. When we are using Alice and Bob for quantum communication, we are not sending any data with them. We are sending only the keys. So, and the keys in case of quantum communication are not available in the beginning. Like in classical communication, we generate a key and we send. So the key is already available. But in quantum communication, you are sending some random data, and ultimately what you get after the communication is a set of key at both sides, which are not available a priori, and they are not even known to anybody. So if the data is lost, then that will not reach to Bob. That means Bob has no recovery of that information. So that data has nothing, no, it doesn't take part in the key generation process. So any losses which are irrecoverable, which cannot be recovered, would not take part in the communication. And this is why the hacker or anybody has an intention not to to lose the information rather to extract the information without knowing Alice and Bob. And also the second part of that was that go there how Alice and Bob know. So as I told you that if now Alice and Bob or the EU has tried to extract the information, and while doing so, as I mentioned, that they will change the quantum state, then Bob will receive a different quantum state than what was sent by Alice. And when they later on do the post processing, they will know that what error has been introduced. If it is above some threshold, then you know that this cannot be done due to the system, but it is because of some hacker. And that is more typically 11%. So if you are close to 11% or more error, then you know that somebody has hacked the information, and then you stop the communication. So this is the idea.
Okay, so the next question is, what about biasing point?
I
What
don't
about
know
biasing?
which biasing point. So this question is not complete, it seems to me.
Yeah, the question is not complete. So we can move on to the next one, which is why not use dual photons in quantum communication?
That is also, I don't know what is dual photons.
Okay,
So not very clear.
probably they are maybe they are maybe entangled photons. I don't know.
No, but entangled we are already using, no? So
Already using.
yeah. Again, this is
There
asking
is
biasing point, but I do not understand what is biasing point, because what we are using, there is no biasing point in our case. We are only using different bases, that is horizontal, vertical, or whatever it is. So that is not biasing point. So it's not very clear what it means.
So there is one question related to hardware. QKD hardware prototype is for educational purpose. May I know the least budget that can generate single photon?
Oh, so that may be taken up later on some other time. I mean, it's not a good idea
Okay.
to. We cannot say about funds required for those things. This is all based on the requirement, basically.
All right. So MDI QKD protocol in what type of transmission methodology? Somebody wants to understand the methodology related to MDI QKD
So
protocol.
I don't know if MDI was talked in this, in this class before, but MDI is a measurement device independent QKD, and this is a specific protocol which is reverse of entanglement based protocol. So in entanglement based, there is an entangled source, and we are sending one photon to Alice, one photon to Bob. In case of MDI, it is reverse. That means Alice and Bob will send a one photon, and in between there will be a measuring device which will measure these two photons in a bell basis. And that is basically, they will make a bell test, and they will make sure that the two photons which are being sent are entangled. And the moment you have entangled them, then you, as I mentioned in the beginning, that entanglement based systems cannot be hacked. So that means Alice and Bob are entangled now, so there is no way anybody can hack or can extract the keys out of them. So they are the most random set of outcomes. So MDI QKD is a very, very important protocol, especially because it it makes sure that any attacks on detector side are not happening. As I showed you, that detector has many attacks. So all these attacks can be removed when you make measurement device independent protocol. And that is a very, very successful protocol. But the problem is that people have tried to develop them, but the rates they are achieving or the distances they are achieving with MDI is very, very small. And that's why people are not preferring them over other kind of protocols.
Okay. So the next question is it possible to test the simulation mode instead of physical lab? And they also want to know the BB84 protocol with 5G communication. Is it possible how to implement the BB84 protocol in 5G communication?
See, first of all, what he's asking is about simulation mode instead of physical lab. See, the problem with quantum system is that they are measurement dependent systems. When you measure only, then you know that the state has collapsed. So you can always simulate, but then the simulation would not be a quantum simulation. It will be a classical simulation. So you cannot, you cannot introduce the measurement dependent randomness in the quantum system, in the simulation, classical simulation. What you will introduce would be some random function, and then it will be still a classical simulation. So this is why we always try to do everything experimentally, where it is the real projection, measurement dependent projection. And what he's asking is research scope how to implement the BB84. That is, I think the people have already done. Even now 6G people are talking about with quantum securities. So I'm sure that that can be available in some literature. I mean, it's not a very new thing or very demanding thing as of now, the BB84. Yeah.
Okay, so the last question is, which is the best method to reduce the Q bar in BB84 protocol?
What is the best method used to reduce the Q bar? See, the Q bar depends on several parameters. I told you that the biggest one is the dark noise. So if you can somehow use detectors which are having very low dark counts, you can reduce Q bar significantly. That's why people are nowadays trying to use superconducting detectors or even very low dark count detectors for QKD. So if you really want to reduce a significant fraction of Q bar, then the first thing would be to use these SNSPDs. The problem is that they are very costly, and that's why the cost becomes a very important factor. The other way to reduce Q bar would be because of dispersion, reducing dispersion. And I also showed that dispersion compensation would be one method. But people are also trying to use other methods. For example, one way to do that is use decoy state BB84, where you purposely put some extra pulses which you already know that what is their nature, and if any eavesdropper detects those photons, then you immediately know that these has been selectively removed, so some attacker is there. So that way you can improve the BB84 kind of protocol. And since BB84 has been the first protocol to do so, so that has been widely explored, and in fact there are commercial devices based on BB84 protocols now.
All right, so there is just, probably we can take the last question, which is, among different transmission mode, which is more effective in quantum communication depends on various approaches, count of photons, protocol, transmitter, receiver, etc.
Yeah, so again, I told you that out of three modes, that is the fiber, free space, and satellite, it is the requirement based outcome. If you want to connect, let us say, two cities, let's say Delhi and Jaipur, then fiber would be a best alternative because the distances are not very large. It's less than 500 kilometers. So fibers would work. But if you want to connect, let's say, Delhi to Kanyakumari, so the distances are significantly large, so fiber would be really very lossy, and the rates would be significantly low. Then in such a large distance you have to go for satellite based communication. If you want to connect two cities or two buildings which are not connected with fiber, or which are, or you want to connect, let us say, one city with the other city which is on a hill and you cannot put a fiber, so in that case the only solution would be a free space communication. So every mode, transmission mode, had its own benefit, and depending on the situations one has to opt for them. In fact, hybrid transmission is the best scenario, because even if you connect with satellites, you have to still use fibers to connect nearby buildings or nearby stations with that. So in that way, all kind of these transmission modes need to be hybridly taken into if you want to make an effective communication, quantum communication.
All right, so thank you, Professor Kanseri, for this talk on fiber optics based quantum communication. And we are thankful to you for taking a valuable time and basically interacting with the participants and solving their queries. And as you can see in the comments, they are appreciating whatever practical demonstrations which you have shown, which are going on in quantum communication. Thank you very much, and hope to see you. Hope to host you in the MNIT in person, probably in some FDPs of futures. Thank you very much.
Yeah, thank you very much. So it was quite